So for those of you who want to attempt the extension question, welcome back, and you can see on the screen the question is already there. So how far from Jupiter is a point where there is no net gravitational field between it and the Sun? Now obviously you need a little bit of data here. The mass of the Sun is on the data sheet, but I'll just give it to you anyway. So mass of the Sun is 1.99 times 10 to the 30 kilograms. Now you'll notice I've used a circle with a dot in to represent the Sun. There are a set of sort of internationally accepted and symbols, shorthand symbols for all the planets. The Sun is a circle with a dot in, just in case you see elsewhere. A circle with a cross in represents the Earth, and Jupiter's symbol is this. It's kind of like a curly 4. It actually, bizarrely, just to give you the history of it, Jupiter of course was one of the Roman gods. One of his symbols was that of the eagle, and that symbol there you can see is the hieroglyphic symbol for eagle. So it's a little bit of a tenuous link, but that symbol there is what we tend to use for Jupiter, and you can look up the other ones as well if you so wish. But anyway, I'm digressing there, which I apologise for. So the mass of Jupiter is 1.90 times 10 to 27 kilograms, and the semi-major axis of orbit for Jupiter is 7.79 times 10 to the 11 meters. So there's all the data you need. What I suggest you do is, obviously, as usual, go away, pause the video, go and have a go at that, see if you can come up with some answers, and then come back and I'll go through those answers for you. So coming back to it then, as usual, it's always best to draw a diagram in these situations. So let's get a diagram going. Obviously this is not to scale, but here we have the Sun and here we have Jupiter. We will say that this distance here we know is 7.79 times 10 to the 11, but at the moment I'm just going to label that as R, and you'll see why later on. Now this point where there's no gravitational field strength will lie roughly there, and what we're being asked to do is to calculate that distance there, which is x. Now with a little bit of very basic maths, we can see that this distance here will therefore be r minus x. Now at this point that we've defined, there will be two gravitational field strengths acting. There will be the gravitational field strength from the Sun acting in that direction, and there will be the gravitational field strength from Jupiter acting in that direction. Now they're acting in opposite directions, but we're looking for where there is no net gravitational field acting, and therefore from a magnitude point of view we just want when the gravitational field strength from the Sun is equal to the gravitational field strength from Jupiter. So bringing it over to a new slide then, gravitational field strength of the Sun is equal to the gravitational field strength of Jupiter. Let's now start forming an equation. So gravitational field strength from the Sun is minus g multiplied by the mass of the Sun divided by, and then the distance from the diagram on the last slide will be r minus x all squared. That's the distance between this point that we're trying to find and the Sun. And that will be equal to minus g times the mass of Jupiter divided by the distance x squared. Now straight away we've got cancellations, negative signs cancel out, and the g's cancel out as well. Fine, not a problem at all. We're happy with that so far. Let's start to plug a couple of numbers in tentatively at the moment. So firstly, mass of the sun, so bringing that from the last slide, so we've got 1.99 times 10 to the 30 over r minus x all squared. We'll leave that as r minus x, and I'll explain why in a moment. And then mass of Jupiter is 1.90 times 10 to the 27 divided by x squared. Now, what we can do straight away on this top line is we've got sort of 10 to the power of stuff that we can cancel out. So if we divide both sides by 10 to the 27, that one disappears. And this 10 to the 30, well, 10 to the 30 divided by 10 to the 27 just works out as, remember, we subtract the indices, so that works out as 10 to the 3. So that just makes that takes that down from 10 to the 30 to 10 to the 3. But of course 1.99 times 10 to the 3 is just 1990. So that's got rid of a decent chunk of standard form for us there. Okay. Next, what we're going to do is we're just going to do some rearrangement then. So we'll cross multiply, that goes up there and that goes up there, and what we're left with then is 1990 x squared is equal to 1.90 multiplied by r minus x all squared. From here then, the rest is just algebra, so we can just crack on and do this on this side there, 1.90, and we can multiply those brackets out. So obviously r minus x all squared gives us r squared plus x squared minus 2rx, and then that therefore gives us 1990 x squared is equal to 1.9 r squared plus 1.9 x squared minus 3.8 rx. Now we can see that we've got the makings of a quadratic here. Remember that r is known, and we'll talk about that in a moment. R is known, x is the unknown, so we've got the x squared terms here and here. Switch back, so if we subtract the 1.9 x squared from both sides, what we end up with is 1988.1 x squared. Okay, our x term is here, so into that we are going to add 3.8r multiplied by x, and then our constants term, x to the 0 term, is this one here, and therefore we're going to subtract 1.9r squared. And then obviously, just to finish that bit of quadratic off, obviously we need to set that equal to 0, and there we have we have a quadratic formula there. Now obviously at this point, if you've got a really sort of top end calculator, you can just start to plug numbers in and it's going to do it for you. If you don't have one of the top end calculators, there are, or even if you do have one of the top end calculators, there are little tricks that you can use in order to make life easier for you. If we have a look on the calculator, one of the sort of little known functions of the calculator is that we've got these letters A, B, C, D, E, F, X, Y and M, which are all on your calculator in sort of pinky reddy ink on that. And you'll notice that you've got this button here, which is the alpha button, which is the letter button. Now actually all 9 of those, so A, B, C, D, E, F, X, Y and M, they are all memories on your calculator, so you can assign values to those letters. So that's exactly what I would want to do in my calculator. Now, in order to do that, you put the number in and you do the following. You press Shift first, then you press the RCL, which is the recall button, but obviously because you've pressed Shift, you'll go to STO, which just means store, and then you'll press the appropriate button. So you can press whatever letter that you want to do. So on my calculator, I did exactly that. I went and set it up. Obviously, A was nice and easy. I just set A as 1988.1. I did the sum then. I did B as 3.8 multiplied by 7.79 times 10 to the 11 and stored that in there. And I did C as minus 1.9 multiplied by 7.79. Apologies there. Running out of space. Times 10 to the 11. So I just stored all of those in my calculator, and then on the next screen I'll show you what I did in order to do my quadratic formula. Now, when you've stored all of those in your calculator's memory, if you just use the alpha and the relevant button, A, B or C, you can start to form an equation. And if you have a look at the top, that's exactly what I've done. You can see that on the screen, I've just done exactly what the quadratic formula is using those letters. At the moment, I've just left it as plus, but of course it doesn't take much to scroll back through and to change that to a minus for your other value. Anyway, once you've done that, and no matter how you've done it, once you've done that in your quadratic, you end up with two answers as normal for a quadratic of this type. We end up with 2.33 times 10 to the 10 metres, and our other answer is minus 2.48 times 10 to the 10 metres. So to bring it back to the context of the question then, if we have the Sun and we have Jupiter, the point that we've found, we were looking for the point which we're doing roughly there, and obviously the distance that we defined was this distance here, which we've basically defined 0 as that distance there, with bizarrely positive going that way for once we're making left positive, so it makes sense that it is this value that we're looking for. So that point is at 2.33 times 10 to the 10 metres from Jupiter. So to take this way beyond A level, what we've found then are 2 points. So we've got 2.33 times 10 to the 10 metres, and we have minus 2.48 times 10 to the 10 metres. Now 2.33 times 10 to the 10 is the answer we wanted, and that was a point there, obviously not to scale, but we get the idea. Now the minus 2.48 times 10 to the 10 would be a point there, and you can see that it's almost exactly opposite but ever so slightly further away. Now what we've done is we've managed to calculate the position of 2 points, and these are two of a set of points known as the Lagrangian points, or you'll hear them also called, just simply called, the Lagrange points. Now these are named after Lagrange, who was a mathematician and an astronomer. He was born in Italy, but later on in his life he became naturalised in France. And Lagrange was one of the forefathers really of the SI system that we use nowadays. Now, as I said, these are a set of points. There are actually 5 of them, and what these Lagrange points do, what they mean, is that they are points where the net force that's acting on an object at that point due to the gravitational force from both the sun and the planet itself. And obviously this would work for a planet and one of its moons as well, where the net force that's acting on an object would be equal to the centripetal force required to keep it orbiting the planet, to keep it orbiting the sun. Now I said that there are 5 of them. We've found what are known as L1 and L2. L3 is actually on exactly the opposite side of the sun to the planet. L4 and L5 are slightly different. L4 is up there, and this is assuming that the planet is rotating or orbiting in that direction, so it precedes the planet, and L5 lags behind. Now L4 and L5 are in a position that if we drew a line from the sun to the point, from the point to the planet, and then obviously drawing up the planet back to the sun, that triangle that I've drawn there would be an equilateral triangle, and obviously exactly the same for L5 down here. Those two would both be equilateral triangles. As I said though, that's way beyond what we need to worry about for A-level, but hopefully I've just stoked a little bit of interest in you there, and I do suggest that you go away, if you are interested in this kind of thing, just go away and read up with it more, and obviously if you've got any questions, just come and have a chat with us, and yeah, we'll let you know some more, at least what myself as a particle physicist know. I can help you out, help you to understand this a little bit more. Anyway, that's the end of this extension video. As I said, I hope you got something useful and interesting out of it, and I'll see you in another video.